Hello, everyone. We're going to continue shortly the theorem we were proving about union of open sets and intersection of open sets. So we'll get to that. So we were about to finish this one. Let me remind you. We wanted to show that the intersection of finitely many open sets is open. And let's remember that an open set is a set where every point has a little a epsilon neighborhood contained in the set. So that's what we needed to do. We picked an arbitrary point. This is this A. And because it's an arbitrary point in the intersection, it belongs to all of them. And because each one of these guys is open, then each one of these sets comes with an epsilon neighborhood, and we called it V sub epsilon I. So this little epsilon neighborhood is contained in the open set OI for each one of the i's between 1 and n. And then we were about to be done. Or the only thing we need to do is to show that we can create an epsilon neighborhood, a smaller one that would fit in all of them. And our idea was to pick the minimum of all of these epsilons. And because there's finitely many, this minimum is greater than 0. So that's good. And then let's check that it works. So why does it work? Well, it works because this epsilon neighborhood centered at A is for sure a subset of epsilon I, right? Think about it. So let's do a little picture. I mean, I did a picture here, like a Venn diagram type of picture, or a two-dimensional one. But in reality, our picture should be like this. Somewhere here is A. And we know that epsilon is the smallest of these. So we have here B epsilon. So if this is epsilon, this one over here is V epsilon A. And because this one is the minimum, that one is inside B epsilon I, right? So this one is perhaps smaller, like in my picture, really small, or maybe it's the minimum, maybe it's a tie. But in any case, this little interval, this little neighborhood, for sure is inside this one, which is what I wrote here. And this one is inside OI. So this is a subset of that, and that itself is a subset of the open set OI. So that means our neighborhood is a subset of all of them. And if you are a subset of all of them, then you're also a subset of the intersection. So from here, it follows that B epsilon A is a subset of the intersection of all the OIs, because it's a subset of each one of them individually. And that's it, because this was, we call this one K. So we're done. Why are we done? We picked an arbitrary point in K, and we show that there's an epsilon neighborhood, which is inside a subset of K. That's the definition of being open, because we did it for an arbitrary point. Thus, K is open. Okay? All right. First little note here is that you really need this to be finite. If you make it infinite, the infinite intersection of open sets may not be open. And you have a problem in the book that asks you about that. I think is the first one, actually. Yeah, part A. I'm sorry, part B. So in part A, they ask, why do you need it to be finite, and where did we use that? And I sort of told you already. And for part B, it asks you to come up with an example where if it's infinite, the intersection may not be open. Okay, good. So this is like the basic property of open sets. And now we're gonna go and talk about closed sets. And we'll tie it up together later on by seeing how open and closed sets are actually related. So here is, now we'll talk about closed sets. Here it comes. First, we're gonna define what it means for something to be a limit point. So a point X is a limit point.
Professor, can I see what's above this?
Above, this was my first page. So you mean what I did before?
Yes, please. Thank you.
Sure. Um, limit point. So what is a limit point? X is a limit point of A if every, this is important, every epsilon neighborhood V sub epsilon X, so centered at X of X, intersects the set A at some point other than X. If you wanted its symbols, all of these that we just wrote, you can write it as follows. You can write it as this neighborhood of radius epsilon centered at X. When you take away X and you intersect with A, is non-empty. So there is someone that belongs to the intersection of these two, and that someone is not equal to X. Okay? Now, an important point in this definition is that the point X may or may not be in A. Okay? This is important. The point X, we're not saying that X has to be in A. So we can talk about limit points of a set, even if the points are not in the set. We'll provide some examples shortly, and maybe this will clarify. Actually, maybe we should start with that example. So for example, what would be a good one here? Well, 0, so little example here. I say that 0 is a limit point of the interval 0, 1. That's my A. Why is that? Why is 0 a limit? Notice 0 is not in here, right? It's not in there. But why is it a limit point? Well, let's draw a figure, draw a picture here. So here's the interval 0, 1. So here's 0 and here's 1. And right now we're talking about the open interval. So it's not including 0 and everything all the way to 1, including 1. That's my interval. Actually, not including 1. Not that it matters, but so this is the interval 0, 1. And why is 0 a limit point? Well, it is a limit point because think about it. If you pick any epsilon neighborhood, no matter how small you pick the epsilon, you're gonna capture some point in here, right? Some point in the interval 0, 1, namely epsilon over 2, for example. See? So note that epsilon over 2 belongs to the epsilon neighborhood centered at 0, right? That always happens. Epsilon over 2 is always in that little neighborhood, and it's also in the interval 0, 1 for epsilon greater than 0, and also epsilon over 2 belongs to the interval 0, 1. So that's it. For every epsilon, I can find a point that belongs to the intersection. So epsilon over 2 belongs to the intersection of 0, 1 and the epsilon neighborhood. And that's the meaning of being a limit point, right? That no matter how small a neighborhood, there will always be a point in the intersection.
Professor, I have a question.
Shoot.
Would like 0.5 be a limit point?
Yes.
Okay, so it also includes points that are inside the set if they have that same qualities.
Yes, exactly. Okay. As long as you satisfy, you may be in the set or you may not be in the set. But I'll tell you one that is not. So for example, 0 is a limit point, but 1.1 is not. 1.1 is not a limit point. Why not? Well, think about it. If you pick 1.1, 1.1 is a little bit over here, right? 1.1. Why is 1.1 doesn't work? Well, because I can find an epsilon that will have no intersection, right? Namely, use epsilon like this big. So use epsilon equals, what do I need? Half of 0.1, so 0.05, right? If I use 0.05, then the neighborhood of radius 0.05 centered at 1.1, if you intersect it with 0.1, you get nothing, right? It has nothing there. So it fails. It fails the property, correct? So, and it's easy to check that something is not a limit point because you only need to find one epsilon that fails. To check that something is a limit point, you need to verify it for every epsilon. So checking that it works is harder than showing it's not. Yes.
Can you repeat what you said about 1.1 not being a limit point?
Sure.
Like, because you can find a point that's not included in something?
You can find a neighborhood, this one over here. You can find some epsilon neighborhood. I made it tiny so that, I mean, if you make it too big, it's not gonna work, right? If you make it too big so that it bites the interval 0, 1, then it's not gonna work. So I need to make it small so that it excludes the interval 0, 1. And I made it small by choosing 0.05, right? This is 0.05. This is half the distance from 1.1 to 1. And then with that one, the neighborhood, if you intersect the interval 0, 1, you get the empty set, right? And you can tell over here that the definition says it should be non-empty, right? It should be non-empty. Okay. Good. Now we have maybe you're wondering why are they called limit points? And that's our first theorem that will probably say why we use that name. Theorem 3.2.5 says the following. It says that a point X is a limit point of A if and only if X is the limit of AN for some sequence AN of elements in A such that AN is never equal to X. So that's why we call them limit points, because they happen to be the limit of some sequence, right? And not just any sequence. So because you could cheat. See, one way of cheating, and we don't want that in the definition, one way of cheating would be to pick as your sequence the sequence that goes like this: X, 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 right? All of them X's. Well, assuming X belongs to A. That cheating would only work if X is an element in A. So if X belongs to A, you could pick the sequence X, 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 right? All of them X's. That would make X the limit of that sequence. But we don't want that because that's not really a sequence of elements in A. You're cheating. You're just using X, right? So we wanted it so that you're not cheating, so that you're using every one but X, right? You could use any elements except X, all right? So this is very simple, and the proof is almost straightforward. Let me see. Let me just check. Yeah, we'll do it. So why is this true? That's an if and only if statement. So we need to do it following the two possible directions. Let me see. I have a couple of questions from the chat. So limit point is when they capture part of the intersection. Yes. And Dranik asks, can you use definition 3.2.4 and theorem 3.25 interchangeably? Yes, that's the right. Now that we know this theorem, now that we're going to prove it, you could use this every time you want to use a limit point. You could use that there is a sequence, right? That's exactly the reason we look at theorems, so that we could use them later on. Okay, so let's go in this direction. So let's assume that X is a limit point. So suppose X is a limit point of A. So now I need to come up with a sequence, right? I need to show that I need to show that X is the limit of some sequence. So I need to create a sequence. How am I going to create a sequence? Well, I need to use the definition of limit point. The definition of limit point is that every time I pick a neighborhood, I can find an element, right? So picture time. So here is my X, and I'm going to pick some neighborhood. And then because it's a limit point, that neighborhood will intersect A. So the neighborhoods that I'm going to pick, just for simplicity, I'm going to use 1, 1/2, 1/3, 1/4, 1/5, because those become smaller and smaller. But you could pick whatever you want. You could pick any other sequence that goes to 0. So I'm going to pick the neighborhood of radius 1. So this is 1. And I know there has to be some element in here of A. Oh, okay. So whatever element of A is in there, I'm going to call it A1. Then I'm going to go and now use my 1/2 neighborhood, right? So this will be now 1/2. And again, by definition of limit point, there must be some element in here from A. I'm going to call it A2. It's somewhere in there. And then I'm going to continue doing that. And that's how I'm going to create my sequence. And then I'm going to show you that that sequence has X as its limit. And and when I pick an element, I'm got to make sure that I don't choose X. And that's easy because I have an entire interval, right? So, I mean, that's not the case. That's the case because by definition, let's go back to the definition. The definition says that I have a neighborhood that intersects A at some point other than X, right? So the intersection is not, it is at some point that is not equal to X. So here we go. So because X is a limit point, using epsilon equals 1/n, there is a point an in A in the neighborhood V 1/n centered at X. And an is not equal to X. That's part of the definition, right? So this intersection, this neighborhood intersects at A at some point that is not equal to X. I just wrote down the definition. Okay, so that's my sequence an. Now, by definition, my sequence is never equal to X. So we got that part already. So the only thing I need to show you, oh, and it's in A, right? So obviously my ANs are in A and they're not equal to X. So all I need to do now is to show you that the limit is AN. How do you show that the limit is, the limit of a sequence is something? You need to, given an epsilon, show that if you go far away enough, then the distance from the number to the limit is less than epsilon. So let's do it. So pick epsilon greater than 0. Okay. So by the Archimedean principle, I know that there is an n. There is n such that 1 over, let me call it capital N, such that 1 over capital N is smaller than epsilon, right? That's the second part of the Archimedean principle, right? That we can create a 1 over n as small as we want. Great. So that's my n that's going to work, because look now at the following. What is it that we need to consider? Suppose that little n is bigger than capital N. Then I want to look at the distance from X to AN. Correct? What is the distance from X to AN? Well, let's remember what the definition of AN was. AN was a point that belonged to this neighborhood, right? So that means that the distance from x to an is at, in the worst case scenario, is how the radius of the neighborhood, right? So this is for sure less than or equal 1 over n, because that's how big this neighborhood is, and an belongs to the neighborhood. So then, because an belongs to the 1 over n neighborhood, this happens. And this one is because little n is bigger than capital N, this is less than 1 over n. And the way I chose capital N, this is less than epsilon. And we are done, right? Given an arbitrary epsilon, I found a capital N such that if little n is bigger than capital N, then this difference is less than epsilon in absolute value. So this means that the limit of the an is x. And we are done with half the proof, right? That's the proof going this way. If something is a limit point, then this sequence exists. Now let's do it the other way around. Now let's suppose that the sequence exists and show it is a limit point. So going backwards, suppose that x equals the limit of an, and an is never equal to x, with an a sequence of elements in capital A. Okay, what do I need to do? I need to show that the intersection of any epsilon neighborhood centered at x intersects the set A at some point other than x itself, right? So let's pick an epsilon. Let epsilon greater than 0 be arbitrary. Again, by the Archimedean principle, there must be an n so that 1 over n is less than epsilon. Do I need that? Hold on a sec. And no, not yet. Okay, I actually don't need that. So let epsilon be arbitrary. And I'm going to use the definition of limit, right? This definition of limit with this epsilon. So what is the meaning of that? It means, so thus, there is some capital N, a natural number, such that if little n is bigger than capital N, then x minus an is less than epsilon. And remember, this is a different way of saying this, is that the number an belongs to the epsilon neighborhood around x. These two things say the same thing, right? And we are done, because if we for this arbitrary epsilon, then I can use a sub capital N, right? So in particular, a sub capital N, because a capital N is greater than or equal capital N. In particular, a sub capital N belongs to the epsilon neighborhood, and it's not equal to x by definition, by the way by our assumption. So because it belongs to this neighborhood and is not equal to x, we just satisfied the definition of being a limit point. Being a limit point means that for every epsilon, you can find a point that intersects the neighborhood b epsilon x with a and is not equal to x. And we got it. It's an is an element in the intersection. So we are done. Thus, x is a limit point of A. And that's the end of our proof. Good. Nice. So a couple of other, so finally we can define closed set, but before we have another definition, and which is this one, 3.2.6. We say that a point A in A, this time is a point in capital A, is an isolated point of A. That's our definition, our term. if it is not a limit point. So intuitively, it makes sense, right? A limit point is a point that has other elements of A nearby, no matter how close you think nearby is, right? No matter how close you think nearby is, there are some other elements in A that are close to A. But isolated means that doesn't happen. Isolated means that you can be by yourself in some neighborhood. You are away from the rest.
Professor,
Yes.
before you continue, you said earlier that in the interval from 0 to 1, that 0 and 1 are not included.
Yes.
So would that make them limit points? It says 0 is a limit point, but if they're not included in the set, it's because they're included in the neighborhood, right?
Oh, so you're talking back to this example?
Yeah.
Yeah, so here 0 is a limit point, even though it's not in the set, right?
Yes.
Yes, 0 is not in the set, but it is a limit point, because if I look at a little neighborhood there, you intersect elements of the other set. Now, if you ask about 1, 1 is also a limit point.
Yes.
But they don't belong to the set. Now, I'll give you a different example now where we have points that are actually in the set, and that are isolated, so you could see. So here's an example. Let's look at our old friend, the sequence 1 over n. So A will be this 1 over n. Yeah, if I were to draw it, it looks like this, right? So there's 1, and then there's 1/2, and then 1/3, and 1/4, 1/5, 1/6, etc. Right? A bunch of points that get closer to 0, but 0 is not in there, right? 0 is not in there. So here, the number 1, for example, here 1 is isolated. Why is 1 isolated? Well, look, I can just look at a neighborhood of 1 where he's by himself, right there. You see? So 1 is isolated. 1/2 is also isolated. I just need to look for a smaller neighborhood, but I can isolate 1/2. Here it is, right? With that little neighborhood, a 1/2 is by itself. In fact, all of these numbers are isolated, right? All of them are isolated. All elements in A are isolated. Okay, now what about 0? 0 is not in A, right? 0 is not an element in A, but 0 is a limit point of A. However, 0 is a limit point of A. Why is it a limit point? Well, it's a limit point because if I look at 0 and I look at any neighborhood, I'm going to intersect A, right? There will be some elements in A that are inside that neighborhood, and that's because of the Archimedean property. No matter how small an epsilon I pick, there will be a 1 over n that is even smaller, right? So because for every epsilon, there is 1 over n smaller than epsilon. So 1 over n belongs to the epsilon neighborhood around 0, intersection A. Okay, so all the points here are isolated. So what are the points that are not isolated then, that belong to the set? Well, if we go back to our previous example of the entire closed interval, this one here, if you pick any number in the interval, for example, 1/2, this guy is a limit point. It is, and it's not isolated, right? Because if I pick neighborhoods around it, it contains, I cannot isolate it from the rest, right? Whatever neighborhood I pick will intersect the set at a point other than himself. So this guy is not isolated. Good. Now, finally, the definition of closed. So what is a closed set? So here it is. Definition 3.2.7. A set F, capital F, is closed if it contains its limit points. So if you have a set that contains all its limit points, then it is closed. All right? So based on this definition and the last examples we consider are not closed, right? So non-examples, let's start with those. Non-examples. This guy is not closed. 0, 1 is not closed. Why is it not closed? Because 0 is a limit point and 0 is not in 0, 1. Boo-hoo, right? A, the set A we just created, the 1 over n, this is also not closed. And why not? Well, because 0 is a limit point. The same reason, because 0 is a limit point and doesn't belong to A. So we better then have some yes examples. So what would be a yes example? So example, well, one yes example is a closed interval. CD is closed for all C less than D real numbers. If you create a closed interval, that set is closed. Why is it closed? Let's prove it, right? Let's do it. Why is it closed? What is it that we need to show? We need to show that it contains all its limit points, right? And for limit point, we can now use our alternative definition. So we could use that every epsilon neighborhood intersects the set at a point other than himself, or we can use that there is a sequence with that limit. And I think we'll use that one. So let's pick a limit point of this guy. So let X be a limit point of CD. What is the meaning of that? Well, we already said it, but I'm going to use the theorem we just proved. So by theorem 3.2.5, there is a sequence. There is some sequence xn that converges to x, such that none of these elements are equal to x. There is a sequence where this happens, and these elements are in CD. And xn is a subset of CD. Right? Okay, and now we got it, because this means then it follows that C is less than or equal xn is less than or equal D. That's the meaning of belonging to this interval, right? It means you are between C and D, including C and including D. But then I can apply limits and what is it? Squeeze theorem, right? So further, the limit of C would be less than or equal than the limit of xn, which would be less than or equal than the limit of D. But this guy is just D. This is a constant sequence, and this is all just D. And this one is X. So what did we just found out? We found out that X is between C and D. So that means that X belongs to the interval CD. And we are done, right? You see that we are done? I picked an arbitrary limit point, and I just proved to you that limit point belongs to the interval. So that means this guy contains all its limit points, therefore it is closed. Thus, CD is closed. Okay. Now, there are other important concepts here. So, for instance, what would be the limit points of the rational numbers? That's an interesting question, right? What are the limit points? What are the limit points of Q, right? So, in other words, what are the limits of sequences that you can create with rational numbers? And the answer is the real numbers. And we have a theorem that explains that. So this is theorem 3.2.10. And it says for every y in the real numbers, there is a sequence of rational numbers that converges to y. Why is this true? Well, it's actually very easy, right? It just comes from something we did before, which is we know the rational numbers are dense. Remember that? In between any two numbers, there's a rational number. So we could do that. So we can pick an R. So here's the proof of this theorem. Pick an arbitrary number. Pick y a real number, an arbitrary one. And then look at the interval y minus 1 over n and y plus 1 over n. So because the rationals are dense, we know that there is some rational number Rn that belongs to y minus 1 over n and y plus 1 over n. Between you take y and you go 1 over n this way, 1 over n that way, and there must be some rational number in there. So let me put intersection Q. So this guy is simultaneously a rational number, and it is between y minus 1 over n and y plus 1 over n. Okay, so that's it, because the way we constructed it, so this sequence satisfies that Rn minus y is less than 1 over n, right, by construction, the way we created it. And these guys are in the rational numbers. So the limit of the Rn is y, and the Rn's are all rational numbers. That means that y is a limit point of the rational numbers. And so every real number is a limit point. So the set of real numbers is the rational numbers, right? So in particular, this tells you, so a corollary of this little thing is that Q is not closed, right? Q is not closed. Why is it not closed? Well, just pick a limit point of Q that is not rational. For example, square root of 2. Square root of 2 is a limit point, but square root of 2 is not in Q. A limit point of Q. Okay, so the set of rational numbers is not closed. This is important. However, remember the one we started the section with, the Cantor set? That Cantor set, believe it or not, is actually closed. And we'll get to know why based on the next few concepts. So I can't tell you right away now because we need to talk about this other concept, which is closure. And let's start with definition. So if you don't have a closed set, how can you make it so that it is closed? That's essentially what we want to address here. And here is the definition. So if you have a set A, given A, a subset of the real numbers, you can talk about its limit points. Let L be the set of limit points of A. The closure of A, denoted A with a bar, is defined as A union L, right? So in other words, to make it a closed set, well, we haven't said that the closure is closed, but that's our next result. Okay, I'm already anticipating it to you. But what this is telling you is that if you have a set, you can add its limit points to it, right? You can put together A and its limit points. And if you do that, that's the closure. And the closure is going to be closed. So that's one way to make a set closed. If it's not closed, you can add the limit points so that you can make it closed. So example, let's do some examples here. So based on what we just did, well, if we do the closure of the rational numbers, well, we get the real numbers, right? Because we said every real number is a limit point of rational numbers. What about the set, this set A? Remember the 1 over n sequence. What is the closure? Well, all the points were isolated, remember, and we only had one limit point. The only point that was a limit point was 0, right? 0 was the only limit point of elements in here. So the closure of A is just A adding 0, right? So we just need to add 1 point, and that makes it happen. So this is actually a closed set, right? One more example. If you do the open interval AB and you do the closure of that, it's going to be the closed interval AB. Because, and we did it for 0, 1, right? That was our first example at the beginning of the class. Let me put it back. So in this example, we said that 0 was a limit point, even though it's not in the set. And 1 was a limit point, even though it's not in the set. So because the endpoints are limit points, you need to add them to make the closure, right? If you add them to the set open interval AB, you get the closed interval AB. And all of these guys on the right happen to be closed. So that's the next theorem, which is that the closure is a closed set. In fact, it's not only any closed set, is the smallest one you can create that contains the original set. I'll explain what I mean by smallest. So here's the theorem. For any A, a subset of the real numbers, A with a bar is a closed set, and it is the smallest closed set containing A. Now, what do I mean by that? In the sense that if B is closed and A is inside B, then A closure is inside B. So if you find any other closed set that contains A, then the closure is even smaller, right? The closure is inside B. All right. So it kind of makes sense. The proof of this theorem is actually one of your exercises in the homework. I believe is 3.7. So I'm not going to do it here. This is exercise 3.2.7. But it's kind of clear, right? I mean, there is a little bit of a subtlety here in the proof that you're going to need to think about. So if you pick a set and you add its limit points, so now A is good. Every limit points of A are good because you added them. So the only thing you need to consider is what if by adding L, now they are new created limit points of A union L, right? What if there are some limit points of the limit points that weren't in here to begin with? And that doesn't happen, but you need to check it, and that's really the only difficulty of the proof. So I won't go into that. What I wanted to talk about is actually the way open and closed sets are related. And this is, you know, the most important part of the section, actually, in my opinion. And they are related by means of complements. And this is actually very awesome because it tells you that, I mean, if you don't like closed sets, you thought open sets were better, good, then you can use complements, and then everything you want to do, you can do it with open sets. If you think the other way around, you like limits of sequences, and you don't like open sets, you thought those were harder, then fine, you can use closed sets and then go back to the open sets via complements. Okay, so let's remember what a complement is. So recall that a complement is the set of real numbers of the elements that do not belong to A, right? The ones that don't belong to A. That's the complement of a set A. And that's all you need to remember, because then the theorem says the following. Theorem, a set O is open if and only if its complement is closed. And it works the other way around, of course. So likewise, F is closed if and only if F complement is open. So if you want to go from open to closed, you just take complements, right? If a set is open, then its complement is closed. And if a set is closed, then its complement is open. Okay? All right. Let's prove this. And in fact, we only need to prove half of this. The other one follows very, so we only need to show that A is open if and only if, I mean, O is open if and only if the complement is closed. Let me explain why first. We only need to show O open if and only if O complement closed. If you already knew this and you wanted to check that F is closed, because if F is closed, then note that F is the same as F complement complement, right? If you complement and then complement again, you end up right where you started, right? So the complement of the complement is that set itself. So then if F is closed, I can use this one and go back, right? So then this would imply, if I already had the first one, I know if something is closed, going backwards tells me that F complement is open, right? So this guy is closed, F is closed, and so that tells me F complement is open. Wow, that's exactly what we wanted to prove, right? And we can also do it the backwards way. If you know F complement is open, so similarly, F complement open implies, this time we're going this way, forward. If something is open, then its complement is closed. So F complement complement is closed, but F complement complement is F itself. Okay, so that's my little explanation of why we only need to do the first part. Open if and only if, O open if and only if, O complement closed. Let's do that. How do we prove that? Okay, so here we go. Let's assume, so first we're gonna go this way. It's gonna go forward. And we're going to assume O is open. Remember the meaning of open? It means every point has a little epsilon neighborhood inside, right? Okay, so now I need to show that the complement is closed. So let's pick a point in the complement, and I need to show, so to show that something is closed, I need to show that it contains all its limit points, right? So let's pick a limit point. Let me write here. We need to show O complement is closed. So how do we do that? We pick a limit point in O complement. Let X be a limit point of O complement. What is the meaning of being a limit point of O complement? That is, for every epsilon, this happens. The epsilon neighborhood centered at X, take away X, intersection O complement is not empty. That's the definition, right? I just wrote down what it means for what is the meaning of a limit point of O complement, right? It means that if you pick an epsilon neighborhood, that intersects O complement in a point that is not X. Okay. So now, what is it that we need to show? We need to show that X belongs to O complement. So if X belongs to O complement, we're happy, right? If X belongs to O complement, we are done. That's what we wanted to show. We wanted to show that every limit point belongs to the set. That's the meaning of being closed. It would mean O complement is closed. So let's analyze what happens if that's not the case, right? So, but if X is not in O complement, what is the meaning of not being in O complement, right? It's like a double negative, right? Not being in the complement actually means being in the set itself, right? And X belongs to O. Okay, and what do I know about O? Well, I know O is open, right? O is open. So I have to use the definition of open, otherwise I'm not getting anywhere, right? So what is the definition of being open? Being open means there is a neighborhood that it's entirely inside O. Because O is open, there is some epsilon zero such that the epsilon zero neighborhood centered at X is inside O. Right? Okay, but if that epsilon zero neighborhood is entirely inside O, then it's not in O complement, right? So maybe let me do a Venn diagram type of picture here, right? I mean, it's better because otherwise my picture is just in a line and you don't probably see anything. So what is the picture that I have here? Well, I have this epsilon neighborhood. This is V epsilon zero centered at X. And all of that is inside O. Let's say that this is O, right? And because it's inside O, then it's not in O complement. Where it's O complement is everything that's outside, right? So if this was all the real numbers, this stuff outside, that's O complement. That would be O complement. Correct? So because my neighborhood is inside O, then it's not in O complement. So this epsilon zero neighborhood, when I intersect O complement, I get empty. Okay, and that bothers me because that's a contradiction. Look at this too. This one says that the intersection is not empty, right? Well, okay, taking away X, but doesn't matter. If you take it away, you have someone. And this one says, even if you don't take away x, the intersection is empty. Well, that's not right. So which one is it? Is it empty or non-empty? It cannot be both. So this is a contradiction. And so that means this case doesn't happen. This is a contradiction. Contradiction to what? Well, because we said if x is not in O complement. So that means x is in O complement. So x belonging to O complement is the only choice. And we are done, right? We just proved that all the limit points of O complement are in O complement. I write a sentence. So because O complement contains all of its limit points, O complement is closed. All right. Good. So that's the end of the proof going this way. Now let's go backwards. So now we're going to assume O complement is closed. Suppose O complement is closed, and I need to show that O is open. How do I show something is open? I pick a point in there and I show it has an epsilon neighborhood inside, right? So I pick a point. Let X be an element of O. Now, being in O means is not in O complement, right? X is not an element in O complement. Okay, and because it's not in O complement, that means it's not a limit point. Because if it was a limit point, if it were a limit point, then it would belong to O complement, because that's the definition of being closed. So let's write here. Note that X is not a limit point. If it were, then because O complement is closed, we would have X belonging to O complement. But X is not in O complement. So that means X is not a limit point. All right? So it's not a limit point. So it fails the definition of being a limit point. What is the meaning of that? Well, the definition of being a limit point is that the intersection of the neighborhood without X is non-empty for every epsilon. So not being a limit point means that there is some epsilon 0 greater than 0, such that the epsilon 0 neighborhood centered at X, take away X, when we intersect that with O complement, is empty, right? I negated the definition, right? What is the negation of some definition? The negation of for every epsilon something happens is there is an epsilon where it doesn't happen. The property doesn't happen. And the property not happening is that this is empty. Okay? All right. So, and we're almost done, because what is the meaning of this? So it again, this picture would help. So we have now some neighborhood. Let's create a picture again. So let's say these are all the real numbers. And this time around, I have, so somewhere in there is O. Let's say this is O. And O complement is what is outside. And I know that my neighborhood, except for X, does not intersect O complement. Right? The intersection with the outside is empty. This is O complement. That's the outside. This is O complement. And this set over here does not intersect the black. It doesn't touch the black. So if it doesn't touch the black, where else could it be? The only place where it could be is inside, right? It has to be in here. This has to be B epsilon 0 centered at X, take away X. Because it does not intersect the black. If it doesn't intersect the black, O complement, then it has to be in O. Hence, this epsilon 0 neighborhood, take away X, has to be inside O. And then maybe you're wondering about the X. Well, that's not a problem because X is in O. And since X is in O, remember, it's right here, X belongs to O. So then this neighborhood without X is in O, and X is also in O. Therefore, the entire epsilon 0 neighborhood, including X, is inside O. And we're done. That's the definition of being open, right? I picked an arbitrary point, and I found an epsilon 0 neighborhood that is inside O. So that shows that O is open. And that's the end of my proof. All right. Questions? Once you know this theorem, by the way, any statement about closed sets, you can make it about open sets and vice versa. And in fact, you could prove everything that we did with any of the proofs we did for closed sets. Now you can go back and actually redo with open sets, right? By just looking at what's the equivalent statement for open sets. In that respect, right, you may remember the one that we started today's class on, right? In today's class, at the very beginning, we finished the proof of the following property. So recall that if you do the union of an arbitrary collection of open sets, so if the OI are open, and you do the union, then the union is open. And if you do an intersection of finitely many of them, that one is also open. So arbitrary union of open sets is open. Finite intersection of open sets is open. We prove that. So now we can, thanks to the Morgan rules, we can now do it for closed sets. So the corresponding statement for closed sets, so for closed sets, works as follows. Assume Ki are closed is a collection of closed sets. Then, if you do the intersection of arbitrarily many, that one will be closed, and the union of finitely many will be closed. And this is very easy to prove. All you need to do is use complements. And remember that the complement of the intersection is the union of the complements, and the union of and the complement of the union is the intersection of the complements, right? So to prove this, use complements and the Morgan's law. The Morgan's laws, which are, like I said, that if you do the union of stuff and you do the complement of that, that's the intersection of the complementary sets, and vice versa. So if you do the intersection and then you do the complement of that, that's the union of the complementary sets. Okay. All right. We have very little time, 5 minutes or so, and I wanted to at least start the last section of chapter 3 that we're going to see, and these are compact sets. All right. And now this is the other topological concept. So we really are only looking at 3 topological concepts when it comes to real numbers. We learn about open sets and closed sets, and the additional one is compact sets, right? So we have to know what is a compact set. And I'll at least start with the definition, and we'll pick it up on Monday. and continue the week after. All right. So compactness. This is the definition of a set being compact, and it's as follows: a set K is compact if every sequence in K has a subsequence that converges to a limit that is also in K. It's kind of like a sweet property to have, right? So it should remind you a little bit of Bolzano-Weierstrass, right? In Bolzano-Weierstrass, we show that every sequence, well, not every sequence, every bounded sequence has a subsequence that converges. So it's a little bit like this. Here you need to show that every sequence has a subsequence, but not only that converges, but that converges to a point that belongs to K, right? So let's see some examples. So one example is the closed interval CD. CD is compact. Why is it compact? Well, think of an arbitrary sequence, right? If you pick an arbitrary sequence in here, it's going to be bounded because it belongs to the interval CD. So because it's bounded, then by Bolzano-Weierstrass theorem, the limit will be by Bolzano-Weierstrass theorem, there will be a subsequence that will be convergent. And then why is the limit in here? The limit will be in here because this set is closed, and a closed set contains all its limit points, right? So this is the little explanation. If xn is a sequence, then it is bounded. So by Bolzano-Weierstrass theorem, it has a convergent subsequence, xn sub k, right? And then this convergent subsequence, the only thing we need to show is that the limit also belongs to CD, and that's easy. And but the limit x equals the limit of x and k is in CD because CD is closed. Remember that a closed set contains all its limit points, and we already know this is a closed set. And because it's closed, it contains X. So that's it. That means this set is compact. All right. So that we have at least some examples of compact sets. And this will also tell you why some others will not work. Like if we make it open CD, will not be compact because our sequence maybe converges to C, right? And if C is not included, then it cannot be a compact set. Okay, I don't want to go over time, so I'm going to stop right here, and we'll continue on Monday talking about this section 3.3.